everyone. I'm Dr. Rizwana, working as a professor of physics in Institute of Aeronautical Engineering. Today we are going to do some problems based on laser. We know that laser light is completely different from normal light. So it has some unique features like directionality, monochromicity, then it is coherent and also it is highly intense beam. And because of its unique features, it has got many applications in day-to-day life. It has many applications, medical applications, industrial applications, scientific applications. And apart from that, it has some applications in science, of course in military, army. So here, now, based on this laser emission, and of course we know that laser, we call it as highly intense. So highly intense means the number of photons emitted per unit area per second will be more compared to any other ordinary light source. So based on this, and of course by making use of formula for wavelength of laser taken in case of semiconductor diode laser, we are going to solve some problems. Now coming to our first problem, here in this case we are considering a semiconductor laser. So what is a semiconductor laser? So in my videos I have discussed about ruby laser and helium neon laser. But what exactly is semiconductor diode laser? Here we know that if we take any type of laser system, it consists of three parts. What are those three parts? Active medium, source of energy, and then we have optical resonator. And based upon what type of active medium we are using, we are going to name lasers. We have different names for lasers based on what type of active medium we are using. And in this case, in case of semiconductor diode laser, active medium chosen is PN junction diode. And the PN junction diode, it is made with some special type of materials. What are those special type of materials? They are called as direct bandgap semiconductors. And actually this direct bandgap semiconductors, they are compound semiconductors where we mix elements coming from different groups. And what is our intention behind making such compound semiconductors? In those semiconductors, if you consider energy gap, what is our energy gap? Our energy gap, suppose if we take energy band diagram, we know that lower permitted band is valence band, higher permitted band is conduction band, and this valence band and conduction band, they are separated by forbidden energy gap. And this, of course, a forbidden energy gap, if EC is the lowermost energy level of conduction band and EV is topmost energy level of valence band, then energy gap, it is given as EC minus EV. But if we consider semiconductor diode laser, where we are making use of PN junction formed with direct bandgap semiconductors, in that case, this energy bandgap, it is equal to energy of photon, right? And what is the energy of photon? It is given as h nu. So nu frequency, if you want to write in terms of wavelength, it will become hc by lambda. So we are going to find energy gap once we were given wavelength, or we can find wavelength once we were given energy gap in case of semiconductor laser diode by making use of this formula. So coming to our first problem, here in this problem, what is the data given? We were given wavelength of laser emitted from a semiconductor diode, which is 1.55 micrometer, and we were asked to find energy gap in electron volts. So we know formula for energy gap in case of semiconductor diode laser, it is given as Eg is equal to h nu, which is equal to hc by lambda, where h is Planck's constant and what is c? C is velocity of light, which is given as 3 into 10 to the power of 8 meters per second. And what is the value of lambda? Lambda is 1.55 micrometer. So micro means 10 to the power of minus 6 meters. And if we want to find Eg, so hc by lambda, I'm going to substitute in place of h as 6.6 into 10 power of minus 34 into 3 into 10 power of 8 meters per second divided by lambda. If we substitute all these values, we'll have our band gap in joules. But if you want our value in electron volts, so here it was asked to get energy gap in electron volts. So what we have to do, this total value in joules, we have to divide it by 1.6 into 10 power of minus 19. So if we do it, then our band gap value, it comes out to be 0.8 electron volts. Then moving further, in this case also we are dealing with semiconductor diode laser. Of course, directly here they didn't mention about a semiconductor diode laser, but we were given gallium arsenide, and gallium arsenide is good example of direct band gap semiconductor which is used in semiconductor diode laser. And we know that in direct band gap semiconductor, their energy gap, it is equal to energy of photon, which is h nu. And in this case, we were given energy band gap value, and we were asked to find what is the wavelength of laser light emitted from this gallium arsenide. Here, of course, band gap, it is given in electron volts. So first we'll convert this band gap into joules by multiplying this value given in electron volts into 1.6 into 10 power of minus 19. So here this band gap formula is Hc by lambda, but we need to find lambda. So this formula, it will get modified. So lambda will be Hc by Eg. So here I made that substituent. What is H? H is 6.6 into 10 power of minus 34. C is 3 into 10 power of 8 divided by what is band gap? 1.44 into 1.6 into 10 power of minus 19. And if we simplify it, it comes out to be 8633 into 10 power of minus 10 meters, and which is equal to 8633 angstroms. Now, next up, coming to this problem. Here, we were asked to find ratio of the simulation rate to spontaneous emission rate for an incandescent lamp which is operating at a temperature of 1000 Kelvin, and we have to assume that operating wavelength is 0.5 micrometer. So here we were asked to find ratio of stimulated emission, rate of stimulated emission to the rate of spontaneous emission. But what is the formula for ratio of stimulated emission to spontaneous emission? This is our formula. 1 by exponential of h nu by kt minus 1. So this is our formula in order to find ratio of stimulated emission rate to the spontaneous emission rate. And what are the parameters given here? Of course, we were given value of lambda, which is 0.5 micrometer. So micro means, if you want to convert it into meters, it will become 0.5 into 10 to the power of minus 6 meters. H value is given, temperature is given 1000 kelvins, and what is the value of Boltzmann constant? It is 1.38 into 10 power of minus 23 joule per Kelvin. And of course, here if we take, now of course we were given value of wavelength, but if we take this formula, in this formula we need value of frequency. So once we know wavelength, we can easily find a frequency by using this formula. So velocity, it is equal to frequency into wavelength. So frequency is velocity by wavelength. And what is the velocity of light? 3 into 10 to the power of 8 divided by wavelength is given as 0.5 into 10 power of minus 6 meters. And if we simplify it, then our frequency, it comes out to be 6 into 10 power of 14 hertz. Now we are going to make use of this formula 1 by exponential. So here we have h nu by kt. What is h? 6.6 into 10 power of minus 34 into, what about the frequency? Just now we have calculated, it is 6 into 10 power of 14 divided by k is Boltzmann constant, which is 1.38 into minus 23 joule per Kelvin into temperature is 1000 kelvins. And this value, entire this value minus 1. So if we simplify it, then this ratio of rate of stimulated emission to spontaneous emission, it comes out to be 3.1 into 10 power of minus 13. Now, here in this formula, we were asked to find relative population of two states. So here we have taken a laser, ruby laser, and here we have two active energy levels. Let us say that first is ground state active energy level E1 and other one is E2. So here we were asked to find relative population of these two states. For that, let us assume that population of ground state, let it be equal to N1, and population of energy state E2, let it be equal to N2. So when we say relative population, we were talking about N2 by N1. And what is the data given? Here we were given wavelength of light, which is 6943 angstroms, and also we were given temperature. Now how to find this relative population? For this, we'll make use of Boltzmann distribution law. According to Boltzmann distribution law, so expression for population, it is given as N is equal to N naught exponential minus E by KT. So here, what is N? N is population of energy state E, and K is Boltzmann constant, and T is temperature. Now, if I want to find, if I want to write expression for population of E1 and E2, if I take E1 here in this place, then I have to replace this N with N1. And if I want to write expression for population for energy state E2, then here in place of E, E2, and in place of N, it should be N2. So here I'm going to get two equations. So first, if I consider population of energy state E1, then my expression for population, it will get modified as N0 exponential minus E1 by KT. And this N2, it will get modified as N0 exponential minus E2 by KT. Now, if we divide this N2 by N1, then this N0 N0 will get cancelled, and we end up having it as minus of E2 minus E1 by KT. But we know that minus of E2 minus E1. So this is E2 minus E1 is nothing but energy of photon, which is h nu. So we'll have hc by lambda. So if we substitute here, so what is our final formula for relative population? So exponential of, here we are going to have minus h nu by KT. Okay, and if you want to write in terms of wavelength, so this formula will become hc by lambda KT, because frequency nu is c by lambda. So here, first I have calculated E2 minus E1 by taking it as hc by lambda. It came out to, and that value we are finding in electron volts. So it means that this value divided by 1.6 into 10 power of minus 19. So if we do it, then our value, it comes out to be 1.79 electron volts. Then N2 by N1 is exponential of this value. So first I have calculated E2 minus E1. This is what we got. And then we have in the denominator KT. Okay, so here also K. So either we can do this E2 minus E1 directly, we can use it in joules. Then we can use our K value in joule per Kelvin. Otherwise, if we are getting this difference in energy level in electron volts, then we have to convert our Boltzmann constant also in electron volts. So for that, what we have to do, what is the value of K? K is 1.38 into 10 power of minus 23 joule per Kelvin. So here this value we have to divide it by 1.6 into 10 power of minus 19 if you want this Boltzmann value in Kelvin. And if we do so, this is the value we are going to get. But simple way is, E2 minus E1 as it is will calculate in joules. So then we have to substitute our Boltzmann constant in joules. So that is the simple way. So when we simplify this value, it comes out to be exponential of minus 69.3, which is equal to 8 into 10 to the power of minus 31. Then going for next problem, here we were given helium neon laser. And this helium neon laser, it is kept at two different distances from the screen. So those distances are 1 meter and 2 meters. And then when helium neon laser, it is kept at 1 meter distance from the screen. Suppose that this is my laser and this is our screen. And when laser light goes and falls on the screen, then it will form one spot. So when this distance is 1 meter, what was the diameter of this spot? This diameter is 4 mm. Whereas if same helium neon laser, if screen is kept at a distance of 2 meters, then what is the diameter of the spot? Diameter is 6 mm. So by taking this parameters, we need to find divergence of helium neon laser. And we know that what is the formula for divergence? It is given as A2 minus A1 by 2 times D2 minus D1. What is A1 and A2? A1 and A2 are diameters, spot diameters at distances D1 and D2. So here diameter of spot which is at distance 2 meter, it is 6 mm. Minus diameter of spot which is at distance 1 meter, it is 4. And because these are in meters, so we have kept them as like we can convert them into millimeters, or we can convert this meter distance into, of course these are the values given in millimeters, and we know that 1 mm is 10 to the power of minus 3 meters. So we are converting these spot diameters into meters. by multiplying it with 10 power of minus 3 divided by 2 into this distances. Already they are given in meters. So 2 minus 1, if we simplify. So what is the divergence of helium neon laser? It comes out to be 10 power of minus 3 radians, which is 1 milliradian. Then next problem. Here we were given helium neon laser. And this helium neon laser, it will emit light whose wavelength is 632.8 nanometer. And also we were given output power of that helium neon laser, which is 2.3 milliwatts. And here we were asked to find how many number of photons are emitted in each minute by this laser when it is operating. So coming to data given, we were given value of wavelength, which is 632.8 nanometers. And if we convert it into meters, so it will become 6328 into 10 power of minus 10 meters, because 1 nano is 10 power of minus 9. And of course, we were given output power, which is 2.3 milliwatts. And if you want to write in watts, what we have to do, we have to multiply it with 10 power of minus 3. And first, in order to find how many number of photons are emitted, first I'll try to find what is the frequency of photon that is being emitted by this helium neon laser. And for that, so we know that frequency, it is given as ratio of velocity by wavelength. So what is the velocity? 3 into 10 power of 8 meters per second divided by, what is the wavelength? Wavelength, it is given as, of course, in nanometer, we have converted into meters as 6328 into 10 power of minus 10 meters. If we simplify, this is the expression for frequency. And once we know frequency, it is easy to find the energy of photon, because energy of photon, it is given as h nu. So Planck's constant into frequency, which will give us this value, which is 3.14 into 10 power of minus 19 joules. Now, of course, power of laser is given. There is nothing but energy emitted by laser. It is in milliwatts. So here, if we convert it into watts, it will become 2.3 into 10 power of minus 3. And 1 watt, it is equal to joule per second. So if you want to convert this energy in minutes, then what we have to do, we have to multiply it with 60. So that will give us energy in minutes, joule per minutes. Now, what is the formula for photons emitted? So, formula for photons emitted is energy emitted by the laser by energy of photon. So, if you do it, then we'll get this number of photons emitted. So, if we divide energy emitted by the laser to the energy of photon, then simply we end up having how many number of photons are emitted per minute. Then, next one. Here also, in this case, just like last problem, here also we were given power of laser, which is 1 milliwatts. And here time is given, which is 10 nanoseconds. And number of photons emitted per second is also given, which is 3.491 into 10 power of 7. And we were asked to find wavelength of laser. So this is the power of laser, and number of photons emitted are 3.4 into 10 to the power of 7. And here, formula, what is the energy of each photon? It is equal to output power of laser beam by number of photons emitted per second. So here output power is 1 into 10 power of minus 3. And then here in this case, of course, we were given how many number of photons are emitted per second. And here we are writing output power as 1 into 10 power of minus 3, and this lasts for 10 nanoseconds. So I have to change this value for 1 second, because we are getting number of photons emitted per second. So even this power also we have to change it per second. So here we are multiplying it with 10 into nanosecond is 10 power of minus 9 seconds. So we need to convert power emitted for 10 nanoseconds to power emitted per second. So that's why we are multiplying it with 10 into 10 power of minus 9. And of course, we have a number of photons emitted per second only. So when we do it, we end up having our energy of photon as 2.8 into 10 power of minus 19 joules. And then, what we are supposed to find? We are supposed to find wavelength of laser, but we know we got only energy of photon. But what is the energy of photon? Energy of photon is h nu. We got this value. I think from this easily we can find wavelength. So wavelength will be hc by energy of each photon. So here is 6.6 into 10 power of minus 34 into 3 into 10 power of 8 by what is the energy of photon we got? 2.86 into 10 power of minus 19. So finally our wavelength, it comes out to be 6942 angstroms. Then coming to our last problem. So here, if we were given a laser which is at thermal equilibrium at temperature 300 kelvins, and of course it has two energy levels which are separated by wavelength 1 micrometer, and we need to find ratio of their population densities. So we have to find N2 by N1. Just now we have calculated N2 by N1. N2 by N1, it comes out to be exponential of minus of E2 minus E1 by KT. But this E2 minus E1, I'll write it as wavelength separation, which is nothing but delta E by KT. And here in this case, because I have energy it is in terms of h nu. So if I want to write, it will become hc by lambda. So if it is delta E, then it will become hc by delta lambda. So this formula, it will get modified as minus delta E by KT into, h into h c by kt into delta lambda. So I'm making use of this formula, and we know wavelength of separation delta lambda is 1 into 10 power of minus 6 meters. We know temperature value, we know h value, and velocity of light value. If we substitute all those values, then our ratio of population densities, it comes out to be 1.46 into 10 power of minus 21. So with this, I'm going to end my session here. Here we have done various problems like how to find the wavelength of laser in a semiconductor diode laser once we were given energy band gap, and also we have seen to find energy band gap once wavelength is given, and we have tried to calculate relative population in terms of once we were given energy separation. And also we have calculated number of photons emitted per second once we know energy of each photon, and of course we know what is the power of the laser. So with this, I'm going to end my session here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.